Hi, everybody. We're going to put a close on Chapter 7, the chapter that is dealing with radicals and radical functions. And we're coming to the last section in Chapter 7, which is 7.7. 7.7 is dealing with complex numbers. And we'll define complex numbers in a moment. But we want to shed a little bit of light as to why this section is needed as we move forward into Chapter 8. As we move forward into Chapter 8, we'll be looking at quadratic equations, quadratic functions. I think we can say, quote unquote, everything quadratic. And item number one I want to mention as we move into 7.7 that's dealing with complex numbers. When we get into Chapter 8, we're going to be solving quadratic equations where we have to find the square root of a negative number. And up to this point, we have only been able to find square roots of non-negative numbers. But we're going to need to be able to find the square root of negative numbers as we move into Chapter 8. And for that reason, we need to develop a new set of numbers. And this new set of numbers is what 7.7 is entitled Complex Numbers. Now, before we define what we mean by complex numbers, we want to talk about the basic unit that is the basis for this new set called complex numbers. And it's called an imaginary unit. The imaginary unit of I. I is going to be the critical letter of the alphabet that 7.7 is going to be dealing with. I stands for the imaginary unit or the imaginary number. And I, like I just said, is going to be the basis for defining what we mean by complex numbers. So, mathematicians have developed a rule using I that will then allow us to find square roots of negative numbers. And here's the premise of what we mean by I. I is equal to the radical of -1. Now, why -1? Because every number is divisible by either a +1 or a -1, and since we're interested in being able to find square roots of negative numbers, the beginning statement is that I is equal to the radical of -1. So if I is equal to the radical of -1, if we square both sides of this equation, we get the second true statement that's going to be very important as we move through 7.7. If you square the left-hand side and you square the right-hand side, squaring the left gives I squared, and remembering back to 7.6, when we were solving radical equations, one key rule in 7.6 is whenever you square a radical, you get the radicand as your answer. So if we square the left-hand side and we get I squared, if we square the right-hand side, we're squaring a radical. And when you square a radical, you get the radicand. So the second true statement is I squared is equal to -1. People, you will need to know these two truths. That's why I have them boxed off. I is equal to the radical of -1. I squared is equal to -1. Now, skill number 1 that we want to look at in terms of 7.7 is to be able to express square roots of negative numbers in terms of I. So when we express these square roots that happen to be negative radicands, we're going to express them in terms of this imaginary unit called I. And when we simplify these, you are as well going to see being demonstrated up here the product rule of radicals. You'll see it momentarily. So let's start with number 1, and let's show you how nice we will be able to find the square root of -64. We need to break this radical expression up into 2 radicals. The first one, the radical of 64 times the radical of -1. We're expressing the square roots of these in terms of I. And since I is equal to the radical of -1, that's why we brought it in here. Because you see 64 times -1 is -64. And now we find the square root of 64, which is 8. And we're going to multiply that by what the radical of -1 is. And since the radical of -1 is I, put them together, and there's our little answer. It's been expressed in terms of I. So 8I is equivalent to the radical of -64. Let's go to number 2. Let's bust it up first. The radical of -11 would be equivalent to the radical of 11 times the radical of -1. Now pay careful attention on this move. The radical of 11 cannot be simplified any further because this does not represent a perfect square, nor does it have any factors that are perfect square. So the radical of 11 is going to stay as is. But the radical of -1 will now be expressed as the imaginary unit I. And now the key thing that I wanted to say. That answer is fine, but the accepted way that we write it, the protocol way that we write it, is to put the I in front of the radical expression. And people, the reason is this. If you put that I too close to the radical of 11, and if it appears that the I becomes part of the radicand, that would be wrong. For that reason, we put the imaginary unit of I in front, multiplied by the radical of 11, and we have our given answer. Okay? Pretty basic, but we have to have new defined terms. Now the radical of -48. Let's begin to do what we did on the prior two. Bust it up. Radical of 48 times radical of -1. However, this time, 48 is not a perfect square like 64 was. 48 is not a number like 11 was, to where you couldn't do anything with 11. We are able to use the product rule of radicals and simplify the radical of 48. So, just let him wait there for a bit. We'll come to him. We need to take that radical of 48 and split it up into two radicals that will multiply together and equal 48, but of which one of them is going to be a perfect square. So I'm going to get this ready right here. And I'm going to pull that 48 off. And like I shared in the prior videos in Chapter 7, we're going to go ahead and prime factor him. Now, for those of you that already happen to know the largest perfect square factor that 48 has, you can put it in there and move right along. But if we're not sure, prime factorization will make it sure to us. So we're going to start with a 2. And it'll divide into 48 24 times. And we'll do another 2, and that'll be 12. And we'll do another 2, and that'll be 6. And we'll do another 2, and we'll get it down to 3. Now, because we're dealing with square root, every 2 of a kind promotes a square. So I'm going to kind of look at this one in this way. That's 2 of a kind. And that's 2 of a kind. This 2 times 2 is 4. That 2 times 2 is 4. 4 times 4, 16 would be the largest perfect square factor for 48. The leftover irrational number of 3 that goes in the irrational house. And now let's begin to put this package together very carefully. There's no need in rushing. Enjoy it a bit. 4 times root 3 times I. We're going to commute, and we're going to multiply 4 times I, and we'll write the final answer as 4I root 3, and it is done. And let's pick up number 4. We started off with 2 radicals. 126, negative 1. 126, we have to see if it can be busted up. So let's just test it first. It's even. So it's got a 2. That'll give us 63. We can't do it by 2 any longer, so we go to the next prime factor, which is 3. And 3 goes into it. And 3 will go into it again. Find 2 of a kind. There's 2 of a kind. So let's begin the split up. I'll get it ready. First one. Second one, the radical of negative 1. 2 3's there. 3 squared, 9. 9 represents the rational number. This is going to be the irrational number found by taking that 2 times that 7. Now let's simplify. 3 times root 14 times I. 3 times I, 3I, root 14, done. What's the skill called? Expressing square roots of negative numbers in terms of I. We're able to simplify it now. Okay. Let's move on. And now let's actually define the set of complex numbers. And here's what we mean. Complex numbers, bullet statement number 1, consists of 2 major subsets. The first subset is the set of real numbers. That's the set of numbers that we've been dealing with all the way up to this section, 7.7. The complex numbers consist of all the real numbers and the imaginary numbers. The imaginary numbers are those numbers that are tied to the imaginary unit of I. It's those two subsets that create the complex numbers. Item number 2. The set of complex numbers are able to be written in a standard form setup. There is a standard form for every complex number, and the standard form is this binomial right here, A plus BI. Like I pointed out here, in this standard form, the first term A is the real number part, if it's there. If it's there. The A represents the real part, or the real number part. The BI represents the imaginary part of the entire standard form of a complex number. A is the real part, BI is the imaginary part. Now, if the value of B is 0, if B is 0, 0 times I would be 0. If B is 0, we would not have an imaginary part, we would only have a real number part. So it says if B is equal to 0, the resulting number is real. The resulting number would represent a real number. And if B is not equal to 0, in other words, the value of B is present. The value of B is not 0. If the value of B does not equal 0, the number is imaginary that you're dealing with. Now here are 3 examples right down here at the bottom. 3 examples of complex numbers, and we'll point it out. -4 plus 6i. The -4 is your A. The positive 6i is your BI. Both the real part and the imaginary part is present. So that means B isn't 0 and A isn't 0. The second one, all we have is the imaginary part. We have the BI. We don't have the A. The A is actually 0. It's actually this. There's your A plus your BI. There is no A. And the last one, all we have is the real number part. The BI is not there because the value of B is 0. It's actually this. It's not there. Now before I leave this, we ordinarily call this binomial expression, we can call it a complex number. We can also simply call it an imaginary unit, an imaginary number, excuse me. Because if I is present in the expression, we can simply call it an imaginary number. This too is an imaginary number. This is a real number. So we want you to remember A plus BI. There's one other thing I want to mention. I'm not going to erase that, but there's one other thing I want to mention about A plus BI. As we move to the next area of problems, we're going to be adding, subtracting, multiplying, and dividing with complex numbers. And when we operate with complex numbers, here's the protocol that we're going to follow. We're going to write our final answers in the standard form, A plus BI. Let me slow that statement down again. We're going to begin to add, then subtract, then multiply, and finally divide with complex numbers. When we arrive at our answer, the answers are going to be written in the standard form of A plus BI. So we're going to move to this. Add, subtract, complex numbers. We're going to do a total of 3 problems. Here is number 1. The quantity of 5 minus 2i added to the quantity of 3 plus 3i. Complex number added to another complex number. Yes, they're binomials. And when we add or subtract complex numbers, we're going to combine like terms. So I'll just start off with this. We're adding, no signs have to change. We'll just bring them right out of their houses. And now, folks, kind of watch what we're going to do. I'm going to commute these terms because I want my final answer to be written in the form of A plus BI. So I'm going to put my real number parts first, and that's 5 plus 3. Then I'm going to bring in the imaginary parts. And now let's write our answer. 8. A negative 2i coupled with a positive 3i plus I. A plus BI. Done. It's straight up. Let's go to number 2. We'll move into subtraction. The quantity 2 plus 6i minus the quantity of 12 minus 4i. I'm going to change the color of blue. We are subtracting. When we're subtracting, the 2 terms in the second quantity are going to have to go through a sign change. So I'm going to insert a distributor of negative 1. And I'm going to get it ready. Down. Distribute that by negative 1. And now let's get it in the format of A plus BI. I'm going to put the real number parts first, then the imaginary. Negative 10 plus 10i, done. No, you are not obligated to take out a GCF. No, we want it in A plus BI form. Done, we've subtracted. One last subtraction one, and then we'll move into multiplication. Just so that you see a third one. The quantity of negative 5 plus 7i minus the quantity of negative 11 minus 6i. It's subtraction. I'm going to insert a negative 1. Negative 5 plus 7i. Negative times negative, positive 11. Negative times negative, positive 6i. Commute. Negative 5 plus 11 plus 7i plus 6i. Negative 5 plus 11, 6 plus 13i, done. Okay. multiplication. Since a plus bi is a binomial, when we are multiplying with complex numbers, we're going to be multiplying with binomials. Or maybe a monomial times a binomial, and we're going to follow the same procedure for those. Let's get the first one written down. 7i times the quantity of 2 minus 9i. People off to the side, I'm going to write this statement. We know that I is equal to the radical of -1. The one that you're going to now have to use is this. I squared is equal to -1. This is key. That is going to be key when we multiply. Here we go. Distribute. 7i times 2. 7i times a -9i. -63i squared. Come down. Bring him down. -63 times the value of I squared. The value of I squared is -1. (14i). -63 times -1, +63. And now if we put it in a plus bi format, it'd be 63 plus 14i, and we have the given answer. If you were to say, what if I by chance on an exam left it in that way, would you mark it wrong? I wouldn't. It's commutative, but we're putting it in the form of a plus bi. It's item number 1. Item 2 will FOIL the quantity of 5 plus 4i times the quantity of 6 minus 7i. We'll do first, outer, inner, and last. 30. Positive times negative. -35i. Inner, positive 24i. Last, -28i squared. Bring him down. Let's combine these like terms. A -35i coupled with a positive 24i, a -11i, then bring carefully down that -28, and that -28 is going to have to be multiplied by the value of I squared, which is -1. We'll then have 30 minus 11i. -28 times -1 would give a positive 28. I'm not going to commute, I'm just going to add them right from here to save a line. 30 added to 28 would give us 58 minus 11i, a plus bi, done. A very basic procedure to do, as long as we are aware of the rules. One last one right in here. The quantity of 7 minus 3i multiplied by the quantity of -2 minus 5i. First terms, -14. Outer, -35i. Inner, positive 6i. Last, positive 15i squared. Down. Combine those two. Negative 29i. Positive 15 times negative 1. Negative 14. Negative 29i. Negative 15. Negative 14 added to negative 15. Negative 29 minus 29i. He's done. Now there's one last little part I want to take care of before we just close this one off. I think it'll be too much to continue to go. I want to make sure that I don't lose the contents of the video. So just one more little item that we want to cover. And it is this. I'll just put it up. It does have to deal with multiplication, so we'll just show it. Now, people, listen very carefully if you would. It appears to be so wanting to use the product rule of radicals and multiply this radical expression times this one and call the answer the radical of 35. But hear this carefully. I'm not writing it down on the board, I'm just going to speak it. The product rule of radicals only works when the radical expressions represent real numbers. If the radicals represent complex numbers, you cannot use the product rule. They cannot be multiplied together. What you have to do is, you have to simplify each one of the radicals first, and then join them together as you move further down. So, we express this in terms of I, and we'll methodically write the radical of 5 times the radical of negative 1, that's him, times the radical of 7 times the radical of negative 1. The radical of 5 is going to stay right where it's at. The radical of negative 1 is going to turn into an I. So let me just write it this way first, then we'll adjust. The radical of 5 times I times the radical of 7 times I. We'll multiply this I with this I, and we'll get I squared times the radical of, now we can multiply them together because they represent real numbers, times the radical of 35. I to the second is negative 1. You can write your answer as negative 1 root 35, or simply the opposite of root 35. Either one of those would fit. Just notice before we just close this portion of 7.7 off, if you were to multiply those two together right away, you would have gotten as an answer the radical of 35. That does not match him. So you see, something would be wrong. And what's wrong is we can't multiply those two together because they don't represent real numbers. We have to express each separate one in terms of I to get our answer. So we'll close this little portion off. We'll come back in the next video and we'll take care of the division and one concluding item of 7.7. Join you in a few minutes. You have a good day. Keep that smile on that face. Bye-bye.